Have you ever really thought about the air around you? I mean, it feels like nothing's there, right? But it's actually a bustling, totally invisible world, and it's full of action. Today, we're going to pull back the curtain on that microscopic world using one of the most powerful ideas in all of physics, the kinetic theory of gases. This is the story of how tiny, unseen particles create the world we see and feel every single day. And this theory helps us answer some pretty common questions. Like, why does a balloon you leave in a hot car swell up like it's about to pop? Or how can you be upstairs in your room and suddenly smell coffee brewing in the kitchen? It's not magic, it's physics. And by the time we're done here, you're going to get exactly how it all works. To solve these little mysteries, we really only need one single powerful idea. The famous physicist Richard Feynman once said it was the most important piece of scientific knowledge we have. And it's this. Everything is made of atoms, these tiny particles that are in constant, unending motion. That right there, that's the key to everything we're talking about today. All right, so let's dive right into that idea of perpetual motion. This is our first clue for understanding how gases behave, and honestly, it's a world of what you might call organized chaos. So what exactly is a gas? Well, picture a gigantic number of molecules, all just whizzing around randomly, constantly. But here's the really crucial part to get. There is a huge amount of empty space between them. We're talking molecules that are often more than 10 times their own size apart from each other. This means they're mostly just zipping along in straight lines until, bam, they hit something. And that freedom to just travel, that's how the smell of coffee makes its way across the entire house. Okay, so we've got trillions of these tiny particles just zipping around everywhere. But what happens when they actually hit something? Like, say, the inside of that balloon. This brings us to our next huge idea, pressure. Let's just break down how this works. Imagine just one single molecule hitting the inside wall of a balloon. As it bounces off, it gives the wall a teeny tiny little push. Now imagine not one, but trillions upon trillions of molecules doing that exact same thing over and over and over, every single second. All of those tiny pushes add up, creating a steady, constant outward force. And that combined force is what we call pressure. So the pressure that's keeping a balloon inflated isn't some kind of static, calm thing. No way. It's the result of a relentless, microscopic storm of collisions. It's just a beautiful example of how massive, observable effects can come from incredibly simple, tiny actions. So we've talked about all these particles moving, but what about how fast they're moving? Well, it turns out the answer is something you deal with every day, even if you didn't know what it really was. Let's talk about the true identity of temperature. The connection is actually super simple. In a cold gas, the molecules are on average just moving slower. They have less energy of motion, what physicists call kinetic energy. In a hot gas, they're zipping around like crazy with way more kinetic energy. So when we use a thermometer to measure temperature, what are we really measuring? We're measuring the average kinetic energy of all those molecules. That's literally it. Hotter is just a simple word we use for faster-moving molecules, and colder just means slower-moving molecules. This is such a fundamental insight. It gives a real physical meaning to the idea of temperature. So now we have all the pieces of the puzzle, right? We've got constantly moving molecules, we've got pressure from their collisions, and now we know that temperature is just a measure of their speed. Let's put it all together and finally solve that mystery of the balloon in the car. And here it is, the aha moment. When you leave a balloon in a hot car, the air molecules inside soak up that heat energy. That makes them move a lot faster. Their temperature goes up. Now, these super fast molecules start slamming into the inner wall of the balloon, both more forcefully and way more often. All that extra pounding increases the internal pressure, which pushes the walls of the balloon outward, and boom, it expands. It's simple, it's elegant, and it's all explained by these tiny moving particles. And this doesn't just work for our balloon example. The kinetic theory perfectly explains all those gas laws that scientists figured out ages ago. Like Boyle's law. If you squeeze a gas into a smaller container, you're crowding all those molecules together. They've got less room to move, so of course they're going to collide with the walls more often. And what happens? The pressure shoots right up. Makes perfect sense. And then there's Charles' law, which is exactly what we saw with our balloon. If you heat a gas up but let it expand, those faster-moving molecules push the container walls outward, increasing the total volume. See? The theory gives us the why behind all of these laws that people observed but didn't fully understand. So this is way bigger than just balloons and the smell of coffee. The idea that a gas is just a swarm of tiny, fast-moving particles is honestly one of the most powerful and successful theories in the history of science. I mean, just look at what this one simple idea does for us. It takes everyday things like pressure and temperature and gives them a real physical meaning down at the molecular level. It explains all those classic gas laws, it even helps us understand more complicated stuff, and, this is amazing, it allows us to actually estimate the size and mass of the molecules themselves. It's truly a cornerstone of modern physics and chemistry. So, we've seen how this theory gives us this incredible lens to understand the free, chaotic world of gases. But that really just leads to the next big question, doesn't it? When all those molecules are packed way closer together, pulling and pushing on each other in liquids and solids, what completely different secrets are waiting to be discovered there?